Okay, hello, ladies and gentlemen. This is Alice. Yeah, I'm so glad to meet you on this platform on I Can Act Talks every Friday. Yeah, we use science talks to connect world and the universe. This is Alice. Yeah, and Beijing. I'm a professor at Peking University. I'm very proud to say that. Yeah, I'm initiated this I Can Act platform. So now it's a very popular platform. Welcome everyone get on board. And this month we have five speakers on the stage. We already have a training and a NACO and the first week for our Young Scientist Award. And the second week we have Anthony Marcus from Rice University. And last week we have Nicholas Kotov. This week we have Raffaella Buonsanti. Yeah, so this was a very, very nice month. Yeah, we have wonderful speakers. And today is the last week of normally the most important week, right? Yeah, we have our speakers and our groups here. So this week we have Professor Raffaella and his partners to jump in for this week's talk. So let me first introduce our super speaker. Yeah, I heard more about he gave a wonderful speech. She gave a wonderful speech. So let me first introduce Professor Raffaella Buonsanti. He is head of a laboratory of nanochemistry and EPFL, Lausanne, Switzerland. He has co-authored almost more than 100 peer-reviewed publications in international journals, and he received the ERC starting grants in 2016 and numerous awards, including the Swiss Chemical Society Werner Prize in 2021. This is important. The Europe Chemistry Society Lecture Award and the Royal Chemistry Society Communication Emerging Investigators Lectureship, both in 2019. Recently, he was awarded an ERC Consolidated Grant, and he's also the chair of the Nanoscience Subdivision of ACS Division of Organic Chemistry, and he's associate editor of ACS Catalyst. Yeah. So let's welcome Professor Buonsanti. Yeah, Professor Buonsanti, the stage is yours, please.
Perfect. Thank you very much, Alice, for the invitation, first of all, and for the kind introduction. It's a great pleasure for me to be here and to share with you some of the science that we have been doing in my group in the past 7 years. So it's a relatively young group compared to many of the excellent speakers that you've also heard this month and also in the past edition of ICANS. So today I will be telling you about how we can advance the chemistry of colloidal nanocrystals to progress in sustainable technologies. Now, if we look at the Sustainable Development Goals of the United Nations, we have that affordable and clean energy and climate action are among them. Now, in order to advance many sustainable technology, we need to design and realize nanomaterials with optimal properties. This is true for catalysis, which I will discuss about because my group is deeply involved into it, but it's also true for batteries or for solar cells and other optoelectronic devices. And when we are looking for eventually achieving best device performance, we really need to tailor-make materials with the tunable morphological characteristics and also in a restricted compositional range so that we can really understand structure properties relationship without any ambiguity. Now, in this scenario, the tunability of colloidal nanocrystals makes them ideal both to discover new phenomena, but has also been shown to provide technological solutions. These colloidal nanocrystals are constituted by an inorganic core and a shell of organic ligands. And the most known colloidal nanocrystals are perhaps quantum dots, where as we change the size, we change their optical properties. And nowadays, quantum dots are embedded into displays. Another class of colloidal nanocrystals are noble metals. Here, the solution of gold nanoparticles appear pink instead of the classical gold color that we know because of the presence of surface plasmon resonance absorption. And here size is important, but also shape. So for example, as we start to make gold nanoparticles in form of rods, their color changes. And these noble metal nanoparticles, because of this surface resonance plasmon absorption, they are integrated in different sensing devices. And I'm not mentioning many other applications that have been enabled by the discovery of colloidal nanocrystals with different composition, different sizes, and different shapes. So there is a lot of activity in this, in research in these nanomaterials. However, what is one of the challenges that we are facing? So one of the problems related to these to nanocrystals, to colloidal nanocrystals, is that their synthesis is still based on empirical knowledge. And so it's often difficult to target and explore classes of materials, which are often those that are required by application. Now, let me share with you how do we synthesize these nanocrystals. So we have metal precursors and organic ligands, and these organic ligands end up functionalizing the surface. The most trivial explanation for shape control is that these ligands bind selectively to certain facets, and thus they determine the shape, for example, as nanorods, if they preferably adhere to a longitudinal facet of this nanorod. In order to explain nucleation and growth, the classical nucleation theory refers to the Lamer diagram, where we have that these monomers, these monomeric species, act as the precursors, and as they reach the critical limiting supersaturation, nucleation occurs and then is followed by the growth. However, one of the issues is that we don't really know what is the chemical nature of these monomers, how the precursors evolve into this monomer, in general, what are the chemical transformations here behind the formation of nanocrystals. And I will argue that it's for this reason that retrosynthesis of materials does not exist, and retrosynthesis of colloidal nanocrystals does not exist, which is different than what organic chemists can do. Organic chemists, they have a molecule in a compound in mind, and then they can selectively break bonds to go to the reagents that they use for the synthesis. We cannot do it in materials chemistry, and we cannot do it for nanocrystals. And the reason is because we don't know much about the chemistry, and the reason why we don't know it is because it's also quite complex. These intermediates can be molecular clusters or coordination polymers or nanoparticles themselves. And so normally we need a miscellany of characterization techniques during the synthesis in order to understand what these intermediates are, and often also to complement this measurement with DFT calculation. However, in my group, we really spend quite substantial effort into this direction, and we demonstrate that if we really are able to understand what the reaction conditions are and what the chemistry behind the formation of nanocrystals is, we can really design more advanced synthesis schemes, and then eventually increase the tunability of materials that already exist, of maybe creating new materials, and in this way contribute to address challenges in sustainable technologies. So today, I will share with you two different topics which highlight the statement that I just made, that to understand the chemistry behind the formation of nanocrystals is crucial to control their function. And I will do that in the case of designing more selective catalysts for the electrochemical CO2 reduction, and then creating new hybrid materials which can be active for different energy conversion processes. So I will start with the first topic about CO2 electroreduction. So why is this important? Now, I mentioned moving towards sustainability, climate action, and energy. And the problem is that the CO2 is increasing in the atmosphere. Most of CO2 comes from the use of coal and oil. So we are moving towards renewable. But the problem with renewables is that they are discontinuous, so we need to store them. And of course, to store renewable energies, we have at our disposal batteries, or what we refer to as artificial photosynthesis. In artificial photosynthesis, the idea is that instead of what plants do is to use CO2 and water to make their nutrients and oxygen. The idea with artificial photosynthesis is instead being able to make chemicals using artificial materials. Now, in the case of CO2, it offers it has a huge potential because we should be able to generate many of the chemicals which are nowadays extracted from petroleum. So it offers basically the potential to revolutionize the chemical industry and build an independence from petroleum while also storing renewable energies. Now, one of the complications and what we are missing now is really a catalyst that is active and selective. Of course, eventually this catalyst needs to be also stable, but the first point to be addressed is to find what can be selective for each of these chemicals. Now, I would like to point out that this is not an easy task. Why it's not an easy task is because the CO2 reduction pathway here is quite complex. And my intention here is not to go through each different pathway, but it's just to give you an idea of such complexity. Of course, scientists working in the field and have been making progress in understanding some of the reaction limiting steps. For example, we can one of the rate limiting step for the formation of CO has been identified to be the first electron transfer for the formation of this CO2 radical anion. We also have come to the conclusion that one of the important intermediates to form methane is CHO, and that CC coupling is needed when we want to form ethylene. More needs to be discovered regarding this reaction pathway. However, this basic knowledge was also sufficient to identify why copper, among other metals, behaves as a special catalyst for CO2 reduction. Because if we start plotting the binding energy of copper towards some of the crucial intermediate that I just mentioned, namely CO and CHO, we see that copper here sits in the middle compared to other metals. And what does it mean is that, and it sits close to this red region, which indicates higher activity towards CO2 reduction beyond CO. Because what happens is that when we have silver and gold, they don't bind CO too strongly, and so the reaction proceeds until CO, and then CO is desorbed from their surface. Instead, some of the other metals here, they get poisoned by CO because they bind CO too strongly. So copper emerges as special. However, the problem here is that if we use a copper foil, so polycrystalline foil, we are going to generate 16 different products, which turns into a selectivity nightmare for separation. Now, studies on single crystals by the now famous researcher, Japanese researcher Hori, evidenced that there is a facet-dependent selectivity of this reaction. In particular, we have that depending on the atomic arrangement of the copper atoms on the surface, the copper can be made more selective, for example, for methane, if we expose the 111 surface, or for ethylene, if we expose the 100 surface. However, these copper single crystals cannot be utilized in actual electrochemical devices, and the high current density required for application. So the first question that my group tried to address was if we could make shape control copper nanocrystals in order to translate these studies from surface science to catalyst behavior under more realistic conditions. So here is where we started, and I'm skipping the deep chemistry insight that I mentioned at the beginning, deep chemistry insight which came from in situ measurement. And thanks to this insight, we were able to synthesize copper spheres of different sizes, copper cubes of different sizes, and copper octahedra of different sizes, and also tetrahedra that were not synthesized up to that moment. I like to point out that here the cubes, they exposed mostly 100 facet on the surface, while the octahedra, they exposed mostly 111 facet, and the spheres have a mixture of both. So what we did was to test then these cubes for the electrochemical CO2 reduction. And what we were expecting at the time, based on the knowledge at the time on single crystals, was that the larger the 100 facets were, the more extended the 100 facets were, and the higher the Faraday efficiency for ethylene was supposed to result from these particles. Instead, this was not what we found. Here I'm reporting the Faraday efficiency versus the size of the particles. The Faraday efficiency is how many electrons are converted into certain products. And this black bar is the hydrogen, which is always hydrogen evolution, which is always competing with the CO2 reduction. And so you can see that compared to copper foil, actually the size of the cubes is important because it needs to be above these 40 nanometer size. And especially what was important is that we found that these 44 nanometer cubes were much more selective for ethylene compared to the other sizes. And we found also an interesting size-dependent selectivity in the case of the octahedra, with the 75 nanometer octahedra being much more selective for methane in this case compared to the others. Now, what changes when we change the size of the nanocrystals? Of course, we change the surface to volume ratio, but that changes in a linear dependence with the size. What else changes is also the ratio between facets, in particular between the edges and the planes. And so what the data were telling us is actually that this ratio between the edges and the facets here actually played an important role in catalysis, in the catalytic conversion of CO2, and was contributing to ethylene selectivity. And this was indeed confirmed by some calculation performed by one colleague of mine here at EPFL, which indeed indicated the importance of these edges. The problem is that as we go too small, then we start having different defects and ethylene selectivity starts to get suppressed. So overall, what we learn from these shape control nanocrystals is that, yes, we can translate these lessons learned from single crystals under more realistic conditions, but we can also go a step beyond because we also start learning that an optimal size exists and that we can relate these optimal size to the presence of edge sites on the particles. Now, because these nanocrystals come as a processible ink, we were also able to integrate them in different types of electrochemical cells. So both to study the fundamental properties in what we refer to as an H cell, but also to integrate them into what are referred to as gas diffusion electrode. In this gas diffusion electrode, we have a porous carbon support, and in this porous carbon support, we can deposit our particles and demonstrate that this selectivity is actually preserved at high current density, which are commercially relevant, like 300 milliampere per centimeter square. So we have still the cubes, which produce mostly ethylene, the octahedra, which produce mostly methane, a mixed product distribution for the spheres, And also, we are also able for because of some synergistic interaction between the catalyst and the device design, we're also able to suppress further hydrogen. And yes, we were able to integrate, working in collaboration with different groups. Here at DTU, we were able to integrate also these particles in different type of electrochemical cells to demonstrate they can also offer a technological solution, that they are not only model system to use. Now, I mentioned that copper is special, and the only problem with copper is the existence of a linear scaling relationship. In order to improve the activity and selectivity of copper, we should be able to, what we want to do is to bring the copper more in the center of this red area, which indicates the higher activity towards CO2RR. Now, why we cannot do it is because these intermediates, they all bind through carbon, and if we want to start moving around with a higher degree of freedom on this map, we have to start to combine copper with different entities. So we should start to play around with the bimetallic catalyst, or maybe with tandem catalysis, which I will explain in one moment what this is about. Or maybe we can start to decouple intermediate via surface functionalization, or also maybe start working with hybrid materials. And so I will show you some example of how we can start doing these thanks to the well-defined control of the system that we have using colloidal chemistry. And what are some of the parameters that become important when we try to boost further the selectivity of copper? And our target are the C2 product. So I mentioned tandem catalysis. The concept behind tandem catalysis is to have a second domain coupled to copper, which is able to reduce CO2 to CO, and then copper further reduces the CO to different products. In this case, we were using silver as the CO generating catalyst coupled to copper. So if we have a simple physical mixture between these two particles, the concept of tandem catalysis does work, as indeed the Faradaic efficiency towards ethylene increases. However, as we started synthesizing what we refer to as heterodimers, where we actually create an intimate interface between the silver and the copper, so they are heteropitaxially attached to each other, what we notice is a further increase of the Faradaic efficiency towards ethylene. Now, we performed some analysis on the as synthesized particles, which revealed that we have a really clean and continuous interface between the two particles. And also we assume, through other characterization techniques, what we found is that there is a charge transfer across this interface, which renders the copper slightly positively charged. And at the time, this slightly positively charged copper was believed to improve the CC coupling because of modulating the absorption energy of CO. So we concluded about the importance of this interface between copper and silver, so that tandem effect could be combined with electronic effect and thus increase even further the CC coupling. Now, having available different shapes of copper, we also started to wonder if we could increase further the selectivity for C2 by maybe coupling the silver spheres with the copper cubes. And what about the copper octahedra? Now, in this case, what we found was an interesting behavior, because both catalysts were able to increase the Faraday efficiency for C2. However, what was interesting to find is that the copper octahedra were selectively preferring ethanol over ethylene. And this was quite of a surprise because normally I just mentioned before that copper octahedra will basically produce only methane. And here is where we performed some DFT calculation in collaboration with Professor Federico Calle-Vallejo. And this calculation, what they showed us is that basically the formation pathway for ethanol proceeds via CH-CO coupling. So it's basically distinguished compared to the ethylene. And this is a key information because then it can give us a clue about how to increase further ethanol production. And indeed, and actually what Federico found is that this intermediate CH-CHO should be even more favored on the edges of the cubes. Now, the reason why we were actually not seeing more ethanol on the cubes was attributed to the fact that the ratio between the facets and the edges was too high. Now, we could demonstrate that we could we could basically increase the contribution of the edges by making copper cubes smaller. So in this follow-up work, we combined different sizes of the cubes with the silver particles. And what we found is that the enhancement factor for ethanol, indeed, when we have small cubes, increases substantially up to 5 times compared to the bigger sizes, because indeed these edge sites do favor, in the presence of a locally high concentration of CO, end up favoring the CO-CH coupling. So this is an example of the design principle that one could obtain by playing around with these well-defined catalysts and how they can lead to enhanced efficiency towards ethylene and ethanol, which are important products in terms of market price and also in terms of energy storage. And we could also, along the same line, for example, move to different materials where with another CO generating metal. In this case, the CO generating metal was zinc. And what we found in this case is that when we have these core shell particles with an alloyed interface containing 19% of zinc, these particles can be actually highly selective for ethanol. So we can make up to 40%. Instead, when we have a much smaller amount of zinc, these particles make only methane. I would like to point out that the stability over time is quite substantial, and so it is the morphology and the composition of this copper zinc oxide, which was revealed by some operando X-ray spectroscopy study. And the way in which, again, we work with the theorists to explain what was behind this, to explain why this was the case, and what they proposed is that actually, as we have only a small percentage of zinc, electronic effects prevail, and these electronic effects stabilize COH intermediate, which are actually favor the methane formation. Instead, as we increase the zinc amount, we start forming clusters of neighboring zinc atoms. And as we form these clusters of neighboring zinc atoms, we start to have a tandem effect combined again to electronic effect, which then eventually favor the CC coupling. So I just provided you 2 examples on how we can start to play around with the metals of these CO generating domains and start to boost the C2 product compared to pure copper by having a tandem effect if we simply make physical mixture of these metals, or we can start to boost them even further if we start to combine tandem and electronic effect. And we can also deviate from the original selectivity if we start synthesizing dilute alloys. So all this information cannot be obtained, so this design principle cannot be obtained unless we are able to synthesize well-defined and tunable materials. And I also would like to add that this solution-based chemistry also enables to go beyond metals and to start maybe combining particles with molecular catalysts. Why is this important? Because molecular catalysts are highly tunables via ligand chemistry. And we can also reduce the potential at which we can more easily reduce the potential that is required to convert CO2 to CO. And this will, of course, be also an improvement that is needed with respect to simply increasing the C2 selectivity. And so what we did here was also to start tuning via ligand chemistry the performance of these iron porphyrin molecular catalyst. So you can basically get with this iron TBTPP, you can get to 100% of CO at close to 100% of CO at potential which are much lower compared to those of silver particles. So silver particles, they do produce CO, but they need a potential at least a minus 0.9 volt versus RH. Now we are able to generate CO at a much lower potential. So what is the result of this? The result of combining this molecular catalyst with copper is that we can start now, if we look at the Faradaic efficiency for ethylene versus the applied potential, we can start to appreciate ethylene at potential which are much lower than the potential at which we can start to detect ethylene for copper cubes. And we can, at the same time, because we have this tandem effect, we can again have enhancement factor which are significant compared to those of the copper cubes without the catalyst. And this is especially true at lower over potential than those that we normally work with, which is more towards minus 1.1 volt versus RH. So this is again versatility offered by the colloidal chemistry, where by changing the size and shape of these nanocrystals, we were able to move beyond single crystals. And now we start learning how to boost further the efficiency of this conversion and the selectivity by combining copper with different elements. But now I want also to move to the second topic that offers a different aspect of the work that we have been doing, which is also about creating new materials for always motivated by improving current technologies and maybe creating solutions for new technologies that are emerging. So in this case, it's about this methodology which we introduced for oxide shells that we refer to as colloidal atomic layer deposition. Now, we started in this case, most of the application was related to quantum dots. I mentioned at the beginning of my presentation about the integration of quantum dots into displays, something that is done by Samsung. Samsung displays are quite important, and I'm sure there are more companies doing that. Of course, these quantum dots are also important for LEDs application and for different light harvesting, such as applications such as photovoltaics, solar cells generation. And again, I don't touch much about the bio application, which are, of course, equally important. And especially for solar cells, actually, the quantum dot-based solar cells are really taking over, have been really taking over in the past 10 years. And one of the advantages is especially the possibility of the processability of these materials. So being able to have them as a ink, a stable ink, which can be processed. Now, one thing one issue of these inks is actually that the ligands that I mentioned at the beginning are in a dynamic equilibrium between the surface of the nanocrystals and the solution. And this dynamic equilibrium eventually causes colloidal instability, both long-term, but also if the solutions are too diluted or too concentrated. And this becomes eventually an issue in the processability of this material. And also, many of these luminescent quantum dots are really sensitive to moisture or to oxygen, and they need to be processed in inert atmosphere. That, of course, can be done, but it will be much more convenient to have them processed in ambient conditions. So we thought at this point, what about being able to have a oxide shell which protects the inner core and also locks this ligand on the surface so that we are able to make colloidally stable inks and to increase, in general, their shelf life. Now, one way to create very thin layers of oxide is atomic layer deposition. This is a technique which is normally performed on thin films. And so, for example, if the goal is to deposit aluminum oxide, first we have trimethyl aluminum and we pulse trimethyl aluminum in the chamber, in the gas chamber of this atomic layer deposition tool. And then this TMA reacts with the surface. Then we purge to eliminate the excess TMA, and then we pulse water that reacts with the TMA, and then eventually the first aluminum oxide layer is formed, and then the cycle can be repeated. Now, we actually tried this atomic layer deposition in the case of these perovskite nanocrystals, which are among those advancing the field of quantum dot-based photovoltaics. And we were able to coat these quantum dot nanocrystals with a layer of aluminum oxide and to keep them relatively stable in ambient conditions, that for sure, and we even demonstrated as proof of concept that they can be stabilized in water. However, in this case, we are making films, and we really wanted to keep our quantum dots as processable inks. And so what we did here was to recognize this limitation of the atomic layer deposition and to turn them into a solution-based process. So basically here, what we have are our nanocrystals in a solution, and then we sequentially add trimethyl aluminum and oxygen in a similar manner of the gas phase atomic layer deposition. And we were able to demonstrate that this approach is applicable to different cores, so to oxide or to metals, and to vary the thickness of the shell with colloidal ALD cycles. So, for example, here, what is possible to see is dynamic like scattering, where the where the radius, the size of the particles increase as we increase the number of layers. We could also estimate the growth per cycle, which approximately is close to an aluminum oxygen bond. So we are making almost a monolayer per each cycle. But then again, we were interested in the chemistry by which these materials nucleate, by which the shell nucleate and grows. And what we found is that if we have the silver nanoparticles, for example, with the oleic acid, the shell can grow. So you don't see it here because it's a thin amorphous shell of oxide. The shell grows also if we have non-oxygen containing ligands, such as amine, but we have surface oxidation of this silver. And then eventually, if we don't have neither the oxygen containing ligands or the oxidation of the surface, eventually the aluminum oxide nucleates homogeneously, but does not form shells around the nanocrystals. So we learned that an oxygen site is needed. and that we need OH basically on the surface, but also that the ligands themselves, so this important component, which is oleic acid in this case, can also act as nucleation site for the trimethyl aluminum. And this was revealed by running some solid-state NMR in collaboration with my colleague Lyndon Emsley. So, but now let's go back to the question. Does this shell really lock the ligands in place and makes more stable inks? So to answer this question, we focus on a class of nanocrystals, of two different classes of nanocrystals, which are normally used in solar cells, namely lead sulfide and perovskite nanocrystals. We grow the shell around them. Again, it's not possible to visualize it in the electron microscopy images. However, what is important to notice is that we don't modify basically the particles when we grow this oxide shell. And then what we tested is the ligand dynamics by performing what we call ligand exchange. So normally you have this long chain oleic acid. When you add a dithiol, which has a stronger affinity for the quantum dot surface, the dithiol exchange with the oleic acid, and you start seeing in NMR, you start seeing the free oleic acid appearing as the dithiol takes its place. On the opposite, when we have this thin shell around the nanoparticles, we really see that the oleic acid remains bound to the surface. And our solutions are indeed much more stable compared to the uncoated sample. And we were also able to demonstrate that these inks can be made at really different concentration, and that we can obtain really uniform films of different thickness, which can then be used for device application. And more recently, we have also extended the concept of these. We have also started to expand the application of this organic-inorganic shell. Is an organic-inorganic because we have the ligands, we have also the oxide network that grows, and now we have learned also that we can start embedding other molecules, so these are organic chromophore, and with this organic chromophore, we can start building assemblies of multichromatic assemblies, basically, including nanocrystals, which absorb light and then can transfer their energy and tunnel this energy outside these hybrid materials. And we are now exploring then eventually the utilization of this energy for catalysis. And we can also see a future implication of the growth of this shell. So for example, we have extremely promising results regarding stabilizing catalysts using these shells. We can also think about grafting different co-catalysts on the surface of the particles, and these co-catalysts can be metals or can be other molecular catalysts, as I mentioned before. And this tunable shell can also be used for completely different application, maybe in optoelectronics, because we have tunability of the thickness, but also we are exploring compositional tuning and other structural tuning of these different shells. And with this, I'll like to wrap up the talk by highlighting again that understanding the chemistry behind the formation of nanocrystals is crucial to control their function. And so that this well-defined catalyst I showed you in the first part of my talk, how we understood that these copper cubes with certain sizes can make much more ethylene compared to a bulk copper foils, and also compared to single crystals especially when we are interested in commercially relevant current density, and how we can start tuning also the selectivity, so we can obtain ethanol and up to 40% of ethanol, which is a state-of-the-art value, as we start to combine copper with different elements. And then I showed you this example of how chemistry coming up with new methods for materials chemistry can solve solution, technological solutions, such as in the case of the stable inks, but also generate materials that we can start to use for other energy harvesting and conversion application. And with these, I conclude where I started, that advancing sustainable technology is a balancing act, and developing this chemistry of well-defined and tunable materials is crucial to advance it. And with this, I like to acknowledge all the present members of the group, also alumni, different collaborators, which are mostly theorists and advanced characterization tools, fundings, and you for your attention.
Wow, wonderful. So Raffaella, it's a really, really nice talk. And yeah, so you have a nice group and very productive. Yeah. So yeah, I'm going to, introduce our panelists and then go to the panel discussion. Okay.
Mm-hmm.
Okay, let me share the screen. Yeah, how nice for this talk. Give us a really, a great picture and also more details. Yeah, in this hot topic. So today we have a great panel. We have Professor Jianfeng Huang, also from Chongqing University, also alumni, right, from Professor Buonsanti's group. So not only on the picture, you see someone real here, right? Yeah. So Professor Jianfeng Huang, also a professor in chemistry at Chongqing University. And he received his PhD in chemistry science from King Abdullah University of Science and Technology, short as COST. And he did his postdoc with Professor Raffaella in during 2016 and 2019. And then he come back to Chongqing University, to China, to Chongqing University. Now his current research interest was focused on designing multi-scale materials for energy research. He was named as one of the 2023 nanoscale emerging investigators. He is also serving as excellency user editors of chemical synthesis. So welcome, Professor Huang. We have another powerful panelist is from Europe, Professor Wander from Professor Wonder-Stem. Yeah, he's a professor, and I hope I read it right. Okay, Utrecht University since 2016. It was obtained his PhD at the same university as 2016, and his expertise is right in this field is nanoparticle synthesis and spectral electrochemistry. And currently, he is leading a group, with very powerful people, to jump in for the panel. And it was named as one of the 2021 nanoscale imaging investigators. And he was invited as part of the upcoming series of chemistry on material in 2023. So welcome, Professor Wonder-Stem. And we have another one very important because it's our challenges. Yeah, every time we have this, very important position. Yeah, I can access stage for each sessions. We invited the young talent, the PhD candidates, or postdocs, to jump in for asking challenge questions. Okay, this time we have Hui Wang as a PhD candidate and Utrecht University, and his supervisor is a panelist, Professor Wonder-Stem, and his research interest is, close to Professor Raffaella's talk. So, let's welcome everyone to jump into our panel, discussions. So, everyone ready? Yeah, please turn on your camera, and let's welcome all of you. Let me see, everyone. Hui, are you ready? Yeah, you are the first one to ask questions. Must be.
Yeah, I'm ready.
challenge question. Okay, please.
Yeah. Thank you, Professor Buonsanti. You have given us a very interesting talk about colloidal and also application of colloidal in catalysis and LED. And I have a question about catalysis, because as we know, catalysis is a kind of surface behavior in liquid, just as CO2 reduction. But for colloidal synthesis, we have a lot of ligands on surface, right? And but does this affect the reduction behavior? If it do, how do they remove this? And also, how can we tell the products of CO2 reduction comes from the ligands and or CO2? Yeah.
Mhm.
This is the first question.
Yeah, it's a very good question, and indeed, this is something that I don't show. I have normally additional slides, but before running the catalysis, we always remove the ligands. So we have learned to remove them either with plasma cleaning or with solvent washing. So some of the ligands they don't bind too strongly to the surface, and so by solvent washing we can remove them. Even if in some cases, if we leave them on the surface, most of them electrostrip. So they are removed from the surface as we apply the cathodic potential needed for CO2, but their amount is so small that doesn't count for the products that we generate. And anyway, as far as we can tell from GC measurement, if we measure the product distribution, when we strip the ligands and when not, it remains pretty much the same. We don't see huge variation.
Yeah. Thank you. And thank you. And another question is that for colloidal synthesis,
of course, you can also design ligands to remain on the surface. So you can also eventually start to use the ligands to modify the behavior if you make sure that the binding of the ligands is strong enough to remain during electrochemistry. So that also opens different opportunities, actually.
So you can also control the ligands, right?
Yeah, right. And we have also a couple of works in that direction.
Yeah, thank you. And another question is, I learned from your slides that for colloidal synthesis, it's very controllable. We can control the shape, and also, as I know, we using colloidal synthesis, we can synthesize very small particles. I just wonder if this synthesis has a limit to, to make big particles like micro scale particles or millimeter scale particles. Is that hard? Or
the problem is that they will start to precipitate while you synthesize them, and so then the process becomes highly inhomogeneous. And so I will say that maybe, we can make like 200 nanometers, but I won't go above that, because then otherwise the process is inhomogeneous. So I will use other methods at that point.
And another question about you make copper and silver for physical mixture, right? And also they have tandem effects. Just like you observe the CO, you observe the CO2 on silver surface and transport to CO, then transport to copper surface. Is that a big distance to transfer?
That is just a drawing. This is just a drawing. You're right. Is how we hypothesize things to happen. Yeah. Then do we know if the CO goes first in solution and then reabsorbs on copper or transfers directly? We don't. In the case of the molecular catalyst was interesting, because what we found is that when the molecular catalyst, so we tested two conditions, the molecular catalyst on a carbon, on carbon particles, and then mixed with the copper cubes, and then the molecular catalyst mixed directly with the copper cube, so an intimate contact. And in that case, we found that actually if you have the molecular catalyst, which still generates CO, but is on the carbon, it suppresses the C2 products. Because, and this what suggests us, is that maybe it is not, in the case of the molecular catalyst, is not a diffusion in the electrolyte and then reabsorption of the CO, but is most likely to be a direct sequential transfer, or maybe a sharing of intermediates. But of course, we don't have much knowledge on the actual surface chemistry that is happening.
Yeah. Okay, thank you.
So these are experimental indications only.
Okay, Hui. Yeah. Okay. Yeah. You sharp questions. Okay. Okay. Yeah. So we have two strong panelists, who is ready, to give some challenges or ask questions or discussions. Jennifer, are you ready? Yeah.
Sure. Yeah. Can you hear me? Yes. Right.
Yeah. Sure.
Okay. So thank you, Alice, for your introduction, and also thank you, Professor Buonsanti, for your fascinating and inspiring talk. Yeah, I really enjoyed it. So I also have two questions here. So the first one, you show the very well defined and isolated nanocrystals in your talk, right? So the feature of such beautiful, well-defined nanocrystal actually remind me of self-assembly of nanocrystals into ordered configurations, which usually requires a high uniformity and homogeneity for nanocrystals. So currently, the particles you show are randomly dispersed on a conductive substrate for example, carbon dioxide reduction. So I was wondering if you ever considered an orderly arranged nanocrystals, for example, by assembling of the same type of particles or even different types of particles. So do you anticipate any difference between order and the disorder configurations for carbon dioxide reduction?
Yeah, it's an interesting question. I think, okay, for sure, for example, loading effects have been shown. So, of course, loading itself might impact then the outcome of the reaction. Then the other thing we might want to consider is that, if they are closer to each other, you might see a different rearrangement, which I didn't touch upon in this presentation during electrochemistry. That can even be beneficial because at some point I thought maybe we can create specific grain boundaries, because in some of the work it has been shown that grain boundaries are important. So if we make self-assemble of well-controlled nanocrystals, that might generate grain boundaries along specific direction while they sinter during electrocatalysis. So it might have a positive outcome, or at least it will advance the current understanding that we have on grain boundaries. So I think it's can be interesting to pursue for different reasons.
Yeah, I agree with you. I think the carbon dioxide is really sensitive to the local environment. So of course, so
it could be impacting the local environment or the eventual reconstruction that comes afterwards.
That's true.
That's another point to keep in mind.
Okay, and my next question is related with the potential technological application. You mentioned the promising potentials of colloidal nanocrystals for carbon dioxide, for example, in gas-fed flow cell, right? So, I mean, somewhat because I once did the work, about the structure evolution of carbon nanocubes during carbon dioxide reduction. So I know the nanocrystals actually undergo very significant structure changes. So personally, I feel that unlike the photonic applications, the electrochemical applications typically involve intense conditions, for example, like high current density or high voltage or somehow. And the nanocrystal might not be so stable enough for a long time. So
I mean, but this is going to be true for all catalysts.
Yeah.
So for all nanocatalysts, now your point, but this is the point made. Well, we're just coming up actually with the one work that was just accepted where we learned that by adding, in this case, we're adding gallium. So I have not discussed the mechanism behind the changes that occur eventually in this catalyst, but we just discovered that the addition of gallium to copper really is able to to make these catalysts morphologically stable up to 20 hours. And we were limited by the flooding of the cell. We also have now another new approach, which really makes these catalysts much more stable. So I think there is space for using the chemistry that we are capable of also to improve the stability, but it's certainly something that we must start looking into in order to really get to what you mentioned, to technological application. And of course, we might also go, and other things we are exploring is more flow chemistry in order to be able then to increase the amounts that we can produce.
So currently, for example, in your mind, do you have any examples of nanocrystal already commercially utilized in electrochemical devices? As far
Colloidal
as
nanocrystal, colloidal is otherwise all the electrochemical cells, they do use particles catalyst. Just that, of course, I mean, they're not synthesized by colloidal chemistry, but I mean, catalysts are particles.
Okay. Okay. Thanks a lot. I learn more from you, and I don't have other questions. Thank you.
Okay, yeah. So after you leave the group, 3 more years, right? Yeah. So a lot of new things was coming out.
I showed a lot of his work actually.
I still think so. That's why Jianfeng, got so many, questions, ideas here. Yeah. So Professor Word, yeah. So you mute? Okay.
Yes.
Yeah.
Yes. Thank you very much, Raffaella, for the wonderful talk. A lot has been said already, and a lot has been asked already. But yeah, as you know, I'm also very interested in everything you do, and also in investigating really these dynamics of the particles that you just already discussed a little bit with John Fang. So, as we know, the magic catalysis happens at the surface, and it's really sensitive to the surface, right? So small changes in the surface chemistry will change the catalysis. And I agree with you that the doping and alloying creates stability. We've seen that empirically. Understanding how and why is maybe a bit more difficult. But if we think of techniques, how to disentangle the surface from the bulk catalyst, let's say, because a lot of the techniques that we use is always a mixture of signals, and this is something I'm struggling with myself, and I would like to hear your opinion on that.
Yeah, it's a great question. You're totally right. And every technique, I personally, I cannot all, is very, I mean, it's a big challenge. It's a huge challenge because the surface, which is the most surface and interfaces, which are the most important component which determine the catalytic activity, are difficult to access while the catalysis is happening. And even more recently, we were trying to understand better this mechanism by which the particles change during CO2RR, and I was even looking for a method which will allow me to probe the electrolyte in close vicinity of the metal. And this is even more challenging. And yeah, I think this is, I'm with you, and I don't have a great answer at the moment, because of course, I mean, the surface sensitive techniques, but what surface? They are not surface really, because they still probe what is below the surface. So yeah, it's a difficult, difficult question. I don't know if you have comments on that on your side.
So my personal opinion on that is that we always need more techniques. We cannot rely on a single technique. So ideally, at least two should be combined.
Even more. Yes.
In the same measurement or in the same environment in different experiments. But ideally, indeed, more. Right. So we work on Raman spectroscopy, for example, which is very surface sensitive. We can probe also things in the electrolyte close to the surface, absorbed at the surface. But it also has its limitations. And you see certain things, but you also don't see other things.
And then
the same holds for the X-ray techniques.
Yeah, well, and often also some of the techniques, they cannot really be performed in the conditions. I mean, some of these techniques that probe the surface, as soon as we start to generate bubbles, we cannot use them. So we cannot often reach the potentials, which are really the interesting one. And then, of course, one can make, assumption and control experiments, but it's never really the potential at which things happen, or maybe the current is lower. So I think the community in general is doing a great job in moving in that direction. But yes, I think combining more techniques is the way to go and try to get a picture. And maybe often we're going to find not a single answer. Maybe we'll open a couple of, we'll leave out a couple of possibilities.
I think we agree, because also you showed also the synergistic effect between the different facets. I fully believe and support that. But the question then is, what happens under reaction conditions to these facets? Are they actually formed in situ if you see an increase over time in ethanol? Because what you start with might not necessarily be what you end up with. And
you're right.
It's a balancing act. So I liked your analogy with the balancing act.
Yeah, you're right.
But this was nice. Yes. And then I asked you this question before, I think, and then your answer was, ideally we make a nano cage out of these cubes, right? Where we only have these 110 facets of the edges and the corners of a cube. Because in the end, the magic is in the synergy.
Yeah.
But what is in your current viewpoint? I think it was 2 years ago that I asked this. What is the optimal catalyst that we need to design for selectivity? Because you show impressive increase in selectivity.
You are right. But now we moved a bit. So my mindset changed in the sense that we also have, because of the stability, I think looking only, also selectivity and stability is a balancing act. This is like life. Nothing is black and white, but we always find gray areas in between. And the same is here. It's like, well, we're trying to optimize this selectivity like crazy. And the nano cages, they might optimize the selectivity, but they're not, their stability, they're not gonna last too long. And so since 2 years, actually, and now we will come up with some work in this direction, that maybe we should, in this idea of a balancing act, we should also start looking at the stability. And so what we can add, which make them stable, and then maybe start learning how to balance the stability and the selectivity. So now we started to look into maybe the same elements that we were adding for selectivity, but keeping more an eye on this design of stable catalyst. So this is how my perspective changed.
Yeah, I think I also agree with that viewpoint. Maybe if I can ask a last question in this direction, because also recently things like pulsed electrolysis have come up, like that actually utilize this dynamics that the catalyst has, and you actually just make it dynamically change over time, which in the end creates kind of a steady state performance by constantly going back and forth. What is your view on that?
I think it's a great approach. The only problem is that, in an actual electrolyzer, that undergoes dynamic, it's not, I'm not sure how implementable is eventually that technology in an electrolyzer, that in an actual electrolyzer, let's say, because you will have to go back and forth, and sometimes you have shutdown and startup that you cannot avoid. So it is an option. I think, as usual, we have to see what can be done in terms of dynamically changing catalysts, and how to maybe learn more how to predict these changes and how to implement these changes in an actual electrolyzer, and how we can make actually more stable catalyst. I think is open now for discussion. We are moving in that direction, and we should see where we go.
Where we end up,
How we end up, yes. I think now we have a few years to watch for these other directions in the field.
Okay, yeah, maybe I ask a questions, as from your advancing. Yeah, actually, most of these technologies, especially now for all this energy topic, yeah, actually, one keyword we couldn't miss is about the cost. Yeah, it's about the cost. Could you please comment on this? How advanced in this case? Yeah, is your technology nanocrystals can be more advancing on cost?
So there was a nice in this article that a very nice cost analysis was performed in these ACS energy letters on solar cells that I showed in one of my slides from NREL, because they are leading the field. And of course, okay, at the moment, if you compare quantum dot-based solar cells and silicon, is still not competitive in terms of cost, but they were also showing progress in that direction. So yeah, at the moment for CO2 electrolysis, there is nothing in terms of cost, module cost, or nothing that I've seen in details, but it's it should come up at some point.
Okay, cool. Yeah, this was always, challenging everyone. Yeah, I think, EPFL have very strong group for the solar cell, right? Yeah, they have a very big impact.
Yeah, it's true.
Yeah.
It's true.
Could you please give some the latest, news of this?
Latest news, I think, I don't know which efficiency we are now for perovskite solar cells. Maybe we are 23%. But also there is always this evolution from looking first for efficiencies and then for stability. Because eventually it has to get to something that is durable. And for now, okay, encapsulation is needed. So I guess in terms of efficiency, is quite happy. They're quite happy where they are with this 23%. And now is the stability challenge also there, and also the substitution of lead. So I guess these are the news from the perovskite world, as far as I know.
Okay, very good. Yeah,
but maybe by the time you come here to visit, things in a few months, maybe things have progressed already.
I hope I can take the solar, airplane.
They exist. Yeah, I mean the solar cells made here, they are outside, so they can be fabricated at least.
Yeah, very, very nice. Actually, Raffaella, I have another question. Is here because all of these panelists, young scientists, as career developing, right, everyone, but you are supermodel, not only a female scientist. I think it's also for the men, they're all looking for, want to, your secret, how you make such a successful, career, and what's your kind of backyard story? Yeah, can share with us, how to go through all this, tough time.
I think they are doing great. That's why I invited them. So because I think they are all promising young scientists, as you mentioned, both of them in nanoscale, and then I read with great pleasure the perspective from wording chemistry of materials, which is what also the reason why I wanted him in this panel. And Zhang Feng is another great scientist. So I think they are doing, I'm not sure they need any advice from me. But in general, it's just, I mean, it's a very enjoyable work. Of course, there are ups and downs, and but overall, it's believing in what we do and doing it with the enthusiasm. Hard work, of course, because to be honest, hard work is needed, and being competitive, but being competitive not with others, but being competitive with ourselves. So trying always to do better, but against our previous selves and not others. This is my, this is also what drives me forward. And curious also about what sometimes we observe. So this is a bit of a summary of what, and also follow a bit what we feel like and what we think is the most important topic that we would like to work on, having an open mind also about listening to other people's opinions sometimes.
Oh yeah, of course. Yeah, that's very important. Yeah, we need to discuss, collaborate and, with others. Sometimes, all these kind of experiences make some new fields, right? Maybe possible some new discoveries. Yeah, that's
it's true.
Very important. Yeah, I think I have another question for the, kind of the, the young scientists is, when you just jump in, to be the tenure track, that time, how you found your new field? I think this is quite challenging,
Well, but my story is a bit different because I've always worked more on the synthesis, but then when I was always providing samples for the application part. And then I got chance to work more directly with engineers as I joined the Joint Center of Artificial Photosynthesis when I was in Berkeley. And so I started to learn more about how to build devices. And in this specific case were electrochemical cells. And then as I started my own group, I decided that was something to pursue within the group so that we could also boost and take advantage more of the materials chemistry that we are able to do. And now we are also expanding more towards the characterization while building up on our core expertise, which is the materials chemistry. But I think also, as the word was mentioning, advanced characterization is also extremely important if then you want to build these structure properties relationship, which are important eventually to advance technology.
Wow, that's very interesting. Yeah, it is cool. Yeah, so I see you graduate from the same university, and now you are being a professor there. Did you feel, stress to find something new?
Not really. No. No, so I think Raffaella also mentioned it that it kind of develops over time. You have to keep an open mind to see different things around you, and then you try to apply what you know to a different field of expertise. And I think Raffaella is a great example of that, at least for myself, I would say. And this is also what I've done over time. So my PhD was in the same university, but completely different group and more focused on the synthesis, also on self-assembly. So I appreciate Feng's comment on the self-assembly, which is something I have in my brain still somewhere to do. And then I developed more in the spectroelectrochemistry aspect during my postdoc, which was in Delft. And then the development towards my current field, which is electrocatalysis and spectroscopy and characterization. This idea kind of originated from just coffee conversations with Wilson Smith in Delft. So he now moved to to the US, back to the US. But he was in the same hallway, and I was showing some things to him, and he was saying like, "Oh, the materials you're making, they're so beautiful. Do you know Raffaella?" Yes, I know Raffaella. I think you can do things like Raffaella is doing, and then add the spectroscopy, and so I really have to give credit to him for pushing me over the line towards the catalysis field, and I'm still happy that I pursued that, and I'm happy that Utrecht gave me the chance to do what I do now with a nice team. Yeah.
Okay, super nice.
It develops over time. It develops over time, I would say.
Yeah, Raffaella be a big supermodel, right? Right. So 2 weeks ago, it's Professor Mikus, Tony Mikus delivered a talk. Then his supervisor, PhD supervisor, Professor Peppers, was in the show. Was asking him very tough questions. So it feels, very stressed. It's if some question answer, okay, my supervisor here. So yeah, it's very interesting. So Jianfeng, you kind of experience different cultures. I see you, China, and then you to go to Middle East, right? Cost is kind of a new university, a totally new setup. Then you go Europe, then you go back. So can you tell us some kind of culture difference, how to affect, your job and maybe some mentor change?
Sure. Yeah. So I think basically the work time is very different. For example, when I was in Coast or you were in Raffaella's group, right? So basically the professors gives very high flexibilities to students or to postdocs, right? They usually kind of like set a goal to you, and then you spend your own time. You decide how to spend your time to finish the goal. So they give really high freedom, and then you can basically do your work, without kind of like too much pressure. So this is somehow a bit different from what I learned, and now also influenced by this sort of like I would say environment. And when I come back to China, I also start
save your words. Okay.
No, I mean I also no. I mean I also try to be like them, to be nice to students. Yeah, and I feel students work actually really hard here. Yeah, so I try to be give them more freedom and more source, more freedom to work. Yeah.
Oh, super nice. Yeah, that's a culture difference, really helpful, right? Yeah. So I think, it's quite, when you are young, you go around the world, you have to know all different peoples, all different mental, thinkings, and how to communication, even different style for communications, right? Yeah, this is really helpful for you make friends and for you understand other cultures. Yeah. How about you? Yeah. So you are now, in a really remote place.
Yeah. Well,
from
think,
Milan, China.
I think I agree with Professor Huang. Yeah. Here, in different culture, we try different food here. It's definitely different from food in China, and also the weather is also different here. Nature also different.
Are you
I think.
okay?
Yeah.
Is he lost?
Yeah. Can you hear me? Yeah. So I think because I like trying new things, so I come here, to try new things since I was young.
Yes, you are.
Yeah, and the advice is don't come for tourists. Don't come to North Europe in winter. Please come here in summer because the winter weather here is not good, but the summer is great. Yeah.
Okay, yeah.
Yeah.
Wow, that's you gave a good ad, for Europe, yeah, to make more fun. Yeah, very, very nice. I think, this time we really want to, have a summer kind of very nice panel discussions because most of our audience are young students, yeah, researchers, and they want to know more about that. Yeah, my last question is for Professor Raffaella. Yeah, it's close to the Women's Day. Yeah, next month. Yeah, early we have an International Women's Day and March 8th. Yeah, so there are a lot of female students, girls, and in our audience. I think many of them really looking forward. How can developing their careers. To jump into be professional. In these kind of directions. So as superstars. So, did you have any words for all these girls?
Well, I don't have advices that are different than those that I gave before, actually. So it's just, work hard towards your goal and be competitive against yourself, and don't care about what people say. It's just go your own direction, and I'm sure you will be successful eventually. So that's all it's needed. Just believe in yourself. But this is true for all young people. So, and surround yourself with positive people that encourage you. So that's also another important point to move forward.
Yeah, positive. I like this one. Last year at 1,000 versions, I think it is June. We invited a superstar. Is a lady. She was from Japan. It was
Jill.
Yeah. Very, very, very good. I think she gave me the best feeling. Is everything response positive.
Mm-hmm.
Everything. Yeah, not only for your research, for the comment, for all these things. Even something looks like very
respond positively. Yes, I agree with
she responds
like, just
positive.
Just positive response, and that's it. And sometimes you might feel uncomfortable for certain situations, but I agree with you. Just keep going and build on those experiences and move on.
Yes. Do remember that response positive. This was not only encouraging yourself, it's encouraging everyone. Yeah. So the one who hear your positive response, they feelings good. This feelings better, right? You even get some power, some energy to go ahead.
Or another advice that I might give is just go for a run, and this helps also release any negative thought that you might have. Going for a run outside.
I see. Yeah. Okay. Very nice. Time flies almost close to the end. Let me share the screen again. As Raffaella, you see this, everyone. Yeah. This was a certification. As everyone, the speakers on this ICANX stage, we deliver this. So this time, electrical versions. Okay, I will email that to you. Yeah, I'm really looking forward to meet you in person. Yeah,
yes, we see you in April.
Yeah, for sure. In 2 months, we will see each other. Yeah. So, all these speakers and panelists, we're planning to get some go together. I think that time we can have more fun because we not just, discuss online in these meeting rooms. We also can discuss downstairs. Yeah, to exchange more ideas.
Correct. Yes.
Yeah. Okay, we're really proud of you. So many nice, work and so many nice, results and so positive support.
Thank you very much, Alice, and thank you also to John Fang and Ward and Wei for being here.
Yeah, so cool. And this was wrap up for this month. Yeah, we have all these super speakers. Actually, Narco was from Switzerland too. Yeah, he is a senior scientist and IDHA. Yeah. So all these months, we really have a lot of fun for these talks. We thank all these speakers. Yeah, many, wonderful, inspiring stories. And next month, we have another super group come up. Yeah, we have 5 weeks here. The first week will be Jonathan and Chang Yong. They are the young scientist awardees, so they will deliver their talks, for the latest, achievements. And the second week is Rosie was from Canada. Yeah, it's a super, stars within the nanotechnologies. And Professor Andrew Alu is going to talk something very interesting, metal material for sound. Yeah, so I don't know what that means, but I'm looking for that talk. Yeah, Patrick Simon was, almost same topics for the energy storage. Yeah, is also focus on the nano structures and all these things. Kelly, Patrice was from France, and Kelly was from Australia National University. She's a super lady too, and she's going to talk about all these technology used for the solar cell. So that will be our March pictures, and I think. We're really looking for all these wonderful talks, and we learn more every Friday. Okay, yeah. So the first one come out is this. Okay, next Friday, yeah, we have 2 young scientists here, and they will show us some very out mind stories. Yeah, some new technologies. We're looking forward to hear them. And next week, the moderator will be Kim, Miso Kim, of Superstars. And so this all for this week. Thank you, everyone. I'm looking forward to have you next week, and keep on, going with ICANX. More things to learn and more things to know, and even more kind of future stars here. Okay, thank you very much. Okay.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中